Continuing with photometry, as the other electroanalytical technique, it's important to remember, why use photometry? One huge advantage, of photometry, and unlike things like chromatography or spectroscopy, is that it can deal with very dirty samples, and some of you have already experienced that. You can take something, like kombucha, and analyze it by photometry, and it handles, dirty samples. You wouldn't be able to do that, you wouldn't be able to inject that, into ICPs or chromatography and so on, because they tend to clog and so forth. So photometry is very handy, in the fact that you don't need to do chromatography, separation, and so on, especially if at all you've got a very specific sensor. I've already mentioned before, another huge advantage of photometry is the fact that you can do speciation, analyte speciation. And analyte speciation means you can differentiate, between oxidation states. And why is that important? Different oxidation states, may have different toxicities if at all you're doing environmental toxicology, or even different oxidation states, may have different types of benefits and so on. So you may need, to differentiate between different oxidation states, of your analyte of interest. Depending on the mode of photometry that you're using, and we're going to talk about modes in the next couple of slides here, you can get very extremely low limits of detection, meaning photometry can be a very selective as well as sensitive analytical tool. Now, you can detect a very wide range of analytical species if you have the right type of sensor. And especially, if at all you've got the right type of potentiostat that can drive the voltage that you need to cause the oxidation or reduction of your analyte. So even though previously people used to say, photometry is very limited only for redox active species, with the right type of photometry in terms of potentiostat, and with the right type, of chemistry, selectivity, if at all you're doing biosensors, so if at all you've got an enzyme, you can analyze, lots of different types of analytes. Like what I showed you before with the glucose. Glucose is somewhat electroactive, but not as robustly electroactive, but if at all you've got glucose oxidase, it can react with glucose to give you a very electroactive species such as hydrogen peroxide. And so, of course, that means, you can play with the chemistry to widen the scope of the types of analytes that can be analyzed by photometry. And as such, it's a very important technique for a very wide range of application: pharmaceuticals, food analytics, environmental analysis, very important in biomedical applications, and so on. And of course, for coatings as well, analysis of coatings. And I'm going to explain in a couple of slides why it's very good technique, for analyzing things like corrosion, coatings, and so on, because actually a surface technique as well. I think I've already said that, it can be very, very sensitive. And lastly, it can be very, very cheap, and, you can make it very, very small into micro scale or nano scale, meaning you can actually do in vivo type of analysis. So you've got a zebrafish and you want to study, the behavior of, say the brain of a zebrafish when you expose it probably to different types of chemicals. You don't need to kill the zebrafish. Actually, you can use nanoscale electrodes, and that way you can do real time, in situ and in vivo, detection of chemical species, in their native environment. So very quickly, let me introduce you, to photometry. You're measuring again current, as a function of applied potential. So you're changing the potential. Remember that you're changing, the potential, the E, or sometimes we call it, the E or the V. Okay, and this allows, oxidation or reduction to happen, at the point when you get to the potential, that is oxidizing or reducing your analyte. Take note of the following. Voltammetry is not quite an equilibrium technique. It is based on the concept, of you've got the electrode and it only analyzes, the analytes, that are attached on the electrode. So that's the electrode, so it only analyzes, the analytes, that get into contact, with the electrode. And as such, things like the surface area of the electrode, become very, very important, because you're only analyzing, the analyte, that comes into contact with it. And how does that happen? So it allows for what you call concentration polarization. And this is what that means. If at all I've got an electrode, and maybe this electrode I connected, to a negative potential of -1V. So the electrode, becomes negatively charged, meaning any species, that are here that are positively charged, for example, very quickly, migrates, onto the surface of the electrode. And that causes, charge, or rather concentration polarization, because these other regions away from, from the electrode, I've got different type of concentration, and there's be a very high concentration, for example, of the analyte, that is touching, the surface of the electrode. And that is what concentration gradient or polarization means, in the case of voltammetry. So it's not really an equilibrium technique, and why that is important is you don't need to waste a lot of time, essentially, for equilibrium to take place. You just need to take an electrode, dip it, onto your sample solution, and, do voltammetry without waiting, for diffusive or convectional, type of forces, to help chemical equilibrium, to ensue. And as such, it becomes a very quick type of technique. And you guys have already seen that in the lab. So what does the setup, look like for voltammetry? As I said before, it's analogous to a galvanic cell. It's actually an electrolytic cell. So you've got two electrodes, you've got an indicator electrode and a reference electrode. And the indicator electrode, remember what we said, is typically, the cathode. And you've got the reference, which is typically the anode. However, in the case of voltammetry, we normally include another electrode which we refer to as auxiliary electrode. So the auxiliary electrode, helps, with the current flow, to make sure the current is only flowing between the working electrode and the auxiliary electrode, and to make sure there is no current, that is flowing, in the reference electrode. And the reason why that is important is, you do not want to change the potential, of the reference electrode. You want it to be fixed. And the way to do that, is to make sure there is no electricity, that is flowing actually, in the reference electrode, okay? And so auxiliary, the current is being measured, is flowing, between the working electrode and the auxiliary electrode, and there is barely any current, that is flowing in the reference electrode. Now the power supply, on the other hand, is applying a voltage, that we talked about, the sweeping, the changing voltage. It's being applied, between the reference electrode and the working electrode. Okay. Now take note of this, that it's an electrolytic cell, and for that reason, you need a potentiostat, which should be a very stable power supply, which is able to very selectively indicate the type of voltage that is flowing. For example, when I say 1.0 V all the way to plus 1.0 V, which is a voltage range, that is almost always analytically useful. That voltage range needs to be very, very stable, meaning I'm very, very specific, to the type of voltage that I'm applying. Now, you see in the industry, people are trying as much as possible to miniaturize potential starts. Other than making them very stable, people are trying to see if they can make them very, very small. And I work, a bit with industries around. What type of industry that I work with, where we are trying to make our own very small, miniaturized, potential start that we can use for our research lab. Because the potential start you guys use or used in the lab, costs around $3,000. All right, which is still a bit expensive. Our goal, is to make a potential that, that can cost around $100, making essentially chemical analysis very inexpensive and accessible, for even other countries, that may not, or other universities in probably some countries, that may not afford, these very expensive types of instrumentation. So let me quickly discuss, about the modes of operation of photometry. Photometry can be ran in 4 different types of modes. Now, the modes refer to how you increase or change the voltage with time. That's what the mode relay is referring to. And so based on that, you would get very different types of signal profiles. The very first type of mode is what you refer to as the linear scan. And this is where you take the voltage and you increase the voltage linearly with time. And for that reason, the type of data, that you actually get, that being current, remember the signal is current, it should typically look something like this. So the signal profile, for a linear scan photometry would look something like that. And I'm going to talk a lot about it, in the next couple of slides. The other type of scan mode is the differential pulse photometry. Differential pulse photometry, you increase the voltage with time, but you pulsate it, so you increase it, in pulses or in steps, okay? So increases in steps, that are slanted. And I'm going to explain why that is very important, in terms of increasing the limits of detection. So in terms of the signal profile that you get, and that's time, it's gonna look something like that. So it's actually a peak, that you get, with differential pulse photometry. So that's a signal profile that you get. And I'm gonna explain later why that's very important, because it's a lot actually easier to integrate peaks, compared, to this kind of sigmoid signal profile that you get with the linear scan. So the other type of mode of photometry is called square wave photometry. And square wave photometry is very similar to differential pulse. The only slight difference is the voltage increases in linear fashion, but you pulsate it, into flat staircases or square staircases, as you go up, with time. And you're gonna see again the type of voltage profile that signal profile that you get, looks very similar, to the differential pulse photometry. So you're gonna see people calling differential pulse photometry as DPV, linear square photometry as SWV, sort of is a very common acronym, for that. The last type of photometry mode, is referred to as cyclic photometry. And cyclic photometry is very similar to linear scan. You can see the voltage increases linearly, and then you switch it back and you decrease it back to where it came from. So for example, if you have minus 1V to plus 1V, so you increase the voltage linearly, and then you sweep it back, from plus 1V to minus 1V. And so the kind of voltage or signal profile, that you get, and that's current again, you would get something that looks like that, and then it looks like that, as you're sweeping back. Okay, so that's called CV, or cyclic photometry. And this is a very important slide, that I'd like you guys to really pay attention to. Now, the working electrode, the indicator electrode, there are many different variations out there, but I'm just gonna focus on two types, of electrodes that are used to make the working electrodes, for photometry. Now, one is the so-called dropping mercury electrode, which is what polarography is, the father of photometry. That's what they really used, to develop the theoretical basis of photometry. So I'm gonna discuss that, briefly, just for you to understand the mechanics of it, because the mechanics of it, is actually what people use to develop all the theory of the modern, type of electrodes that we use. I guess I'm gonna call these modern type of electrodes, solid state electrodes, that we use, in photometry. So the other types of electrodes really are things like, platinum. You can use gold, but of course platinum and gold, they are fairly expensive. So I think the most now prevalent type of electrodes are the carbon-based electrodes, something like graphite, which is very inexpensive. You guys used carbon nanotubes, which is another allotrope of carbon, which is a lot more conductive compared to graphite. You can also use glass carbon electrode, which is very, very common in the lab. And you can also use other allotropes, of carbon, other forms of carbon, things like graphene oxide, it's becoming another very common type of material, that has got very superior conductive properties. So you can see actually, carbon is dominating, the field of electrochemistry as far as the type of a solid state electrode that can be used. So let me quickly, talk about, the nature of the signal profiles that you get, and that is what we refer to as the photometers. The signal that you get, which is current as a function of voltage, is what you refer to as, a photometer. Now, when you're dealing with a linear sweep, as I said, now you get a profile, a signal profile that looks like a sigmoid curve. And look at some of the features of it. You get to a point, in fact it looks almost like a titration curve. You can see it looks very similar, right, to the titration curve. You get to the end, of the current increase, and that is what they refer to as a limiting current, meaning you no longer have any analyte, that is touching, that is an electrode. You no longer have any analyte, that is touching the electrode, because it's already been oxidized or it has been reduced. So that is a limiting current, meaning it's plateauing off because you no longer have any analyte, that is that is touching the electrode surface. Of course, you can see initially here when you're starting the voltage run, there's no current because there's nothing, that is being oxidized. And as you increase the voltage, you get oxidation happening, and so the current keep increasing. And as it is increasing, you're depleting, the amount of analyte that is present until one is completely depleted. And so there's no current that is being generated any longer. And so the signal then, would be the gap between this background, and the limiting current. And essentially, that is going to be your limiting, that's going to be your signal, that you actually plot. The IL is going to be your signal that you plot, which is that gap, between the limiting current, and the background current. So in discussing the mechanism of transport, how you're transporting, the sample, from the bulk, this is a bulk solution, sample solution. And then you've got an electrode. The electrode can be very, very small, even micro electrodes like what you guys have been using in the lab. How do analytes, migrate, from, the bulk solution all the way, to the sensor, for them, to get probably, oxidized, for them to get probably oxidized, and for you to be able to detect the signal. So there are three forms of migration, that can take place. Now there's diffusion, where the analyte, migrates, of course, from the region of, high concentration, to the low concentration. And, you can also have, convection. And convection, it's when you introduce a form of stirring, so you're creating turbulence, turbulence in the sample solution, and that is convection. Now, another type of migration, which is not actually desirable, but it's always there, is what you refer to as migration, due to electrostatic, attraction. And as I said before, if you have an electrode, the electrode is going to be polarized, probably is going to be positively charged if you apply a positive potential. And for that reason, any anions, that are present, say chloride, they're going to migrate very, very quickly, because of that electrostatic attraction of different, different charges, the positive charges attracting the negative charges. And that is what you refer to as migration. Now, migration is not desirable because it's the basis of what you refer to as the charging current that is always present, in voltammetry. And so it's actually noise. This one is related to noise. Because remember, you've got an electrolyte, that is already present in your sample. And an electrolyte, consists of anions and cations. So if you apply, a voltage on your electrode, the oppositely charged, ions, migrate very quickly, generating electricity, generating current, associated with that. So you can see that is noise that you really do not want, or what people refer to as a charging current that should be avoided. And I'm going to explain, why it's actually the basis of why people decided to change to different types of modes so that you can get rid of these migration this migration effect, or the charging current. So some people call this actually non-Faradaic, current, because it's not related, to any redox process. It's only related, to migration of the ions, the non-Faradaic current. But in this case, we are interested, of course, with the Faradaic, Faradaic current, which is a signal of interest. So hydrodynamic voltammetry, refers, to when you are actually increasing the transport of your analyte, by stirring. Okay, all right. So anytime you are doing convection, meaning you are either rotating, the electrode, or maybe you even put in a star bar, so that you can increase, the movement of the analyte from the bulk solution, to the surface of the electrode. You call that type of technique, hydrodynamic voltammetry. So hydrodynamic voltammetry, assists again in moving the analyte, from the bulk to what you refer to as the nast layer. Now, the nast layer is the only region, where the analyte is touching the electrode, and that is getting oxidized or reduced. So the electrode only really does the analysis, of analytes, that are in the nast layer, in the nast diffusion layer, as they call it. The nast diffusion layer, can be very, very thin, probably around, 100 microns, so very, very thin. But with hydrodynamic photometry, it really helps, in assisting, the migration of the analyte, into the NAST layer, to improve, the limits of detection, and so on. But you're gonna see, most of optometry actually is done, without doing the hydrodynamic photometry, meaning you're not assisting the mass migration of the analytes by convection. And so the movement is purely limited by diffusion. And so you're gonna see this, in most cases, the current, is really limited, by diffusion. So if you look at the relationship of what is happening in photometry based on these equation, the current, that you generate from the oxidation or reduction is proportional, to the concentration, and the proportionality constant, are all these variables, that actually affect, photometry. If I ask you, some of the parameters that you need to optimize in photometry, to give you the best results, you look at these equations and look at these variables, that you need to play with, so that you can improve the limits of detection, which is a signal in photometry. A good example, is surface area of the electrode. It really affects the current. And so you need a very high surface area, high surface area of the electrode, for you to get a very good signal. Now, as it were, electrode surfaces increases as the volume decreases. I hope you guys know that, that the area actually increases, as the volume, actually decreases. And that's why if at all you've got a microelectrode or a nanoelectrode, they have often very high surface area to volume ratio. And so the smaller the electrode actually, the higher the surface area. All right. And so you can see again that parameter, surface area, is what you really need to play with, when you're trying to modify or create, an electrode. Things like diffusion coefficient of the analyte. If at all the analyte is very, very bulky, it diffuses slower, to the electrode. And so the molecular weight or the diffusion coefficient really of the analyte equally affects, the limit of detection or the current, that is generated. So things like, the NAST diffusion layer, again, I talked a lot about that. You can improve the thickness of the NAST diffusion layer, by using convection, okay? The problem of doing convection is you introduce irreproducibilities, inside your electrochemical cell, and that's why it's sometimes a problem, to do convection and so forth, all right? Now, you can see this other equation here where the voltage, of your the voltage of the voltage of your electrochemical cell is proportional, of course, to the current, based on, variables in the NAST equation. You can see that. You can see this is, the standard electrode potential, the E half, and N, of course, is the number of electrons, that are being transferred in the redox process. I, is a current, at each point as a voltage increases, and IL is a limiting current, and I, again, is a current. So again, you can see the relationship between the NAST layer or the NAST equation to some extent, and photometry. And so you can see the intersect, right there. So what are the types of currents out there? I think I've already mentioned, you're interested with the Faraday current, so that is the analytical signal of interest. But unfortunately, I said there is migration also taking place, when you apply a voltage into a solution that has got an electrolyte, and migration takes place because of this electrostatic attraction of ions being attracted to the positively or the negatively or oppositely charged form. And because of that, you create the non-Faradaic, or what you refer to as a charging current, the charging current. And so charging current is noise, and it should be avoided. So when you're doing linear sweep, photometry, which is sort of, where polarography started, where you're using dropping mercury electrode. So your profile would typically look, like that, okay? And, you can, determine, for example, the oxygen, that is present in solution, just by looking at, the appropriate voltage, that causes the, the oxidation of oxygen, or rather the reduction of oxygen, into hydrogen peroxide. But you can see also the hydrogen peroxide equally undergoes reduction again at this potential around -1. And so you get this other reaction that is taking place. So the reason I said this is because, while it could be useful for use as an oxygen sensor, unfortunately, in most cases, is actually noise as well, because you're gonna see oxygen is dissolved in most of the samples, that you're working with, in the solutions that you're working with. And so you're gonna see the oxygen waves, if at all you're not interested in that at all, then they actually interfere, with your detection in photometry, because of this because oxygen is an electroactive species, with two redox steps, from oxygen being converted to peroxide, and peroxide again being converted, or reduced, into water. And so there can be noise, if at all you've got oxygen that's actually dissolved in your samples. So the solution to this often is to bubble nitrogen, into your samples, so that you can remove, most of the oxygen that is actually present. Of course, unless, you're actually interested in determining the oxygen. And so the equations that I gave you in the previous slide, the oxygen redox processes, are actually the basis for this type of sensor, called the Clark oxygen sensor, that one of the students, Salia, you are using in the lab, is based on that concept, okay? So, but as I said, it is a problem, if at all you're not interested in the oxygen, and so you need to get rid of the oxygen. So other applications, of hydrodynamic photometry, you can use it as a way to detect the add point, in amperometric titration curves. You can also use it to detect almost anything when you're doing HPLC. So HPLC, you can do liquid chromatography, and the detector can actually be photometry as well, especially amperometry. It can be amperometry, as a detector. So as you're gonna see, and it's very important, I talk a little bit about polarography again, because the basis of it is what evolved, into these other type of other electrodes. But the theory, was the theory of photometry, was generated, by doing polarography. And as I mentioned, polarography is where you're using the dropping mercury electrode, as your electrode. And you can see how important it is. As I said before, the gentleman who developed it, actually won a Nobel Prize. So in this case, you limit convection. You do not do convection at all, when you're doing polarography. And the reason for that is that dropping mercury, it's gonna be very unstable, if at all there is any mixing, or any turbulence, that is happening inside the sample solution. So in photometry in general, other than hydrodynamic photometry, we do not do any mixing at all. And so the limiting current that I talked about, where the current, is flattening in that sigmoid curve here, that limiting current, is dependent, on the ability of the analyte, to diffuse, to the electrode surface. So the dropping mercury electrode setup, looks like this, where you've got a capillary, and inside that capillary you fill it up with mercury, and that capillary has got a hole. And so mercury, droplet keeps growing, and then it drops off. And now you dip this electrode, inside, the sample, okay? So you can see the mercury drop keeps growing as you, of course, are applying, voltage to it. You're doing electrochemistry. The drop keeps growing until it becomes too big, and then it drops off. And so based on that, you can see the signal profile will keep increasing, gets to the limiting range, and then it falls back to zero. And the reason it's falling back to zero is because the electrode, has been knocked out. That drop has been knocked out. And so you now have another fresh drop. You do electrochemistry. The drop grows. You get to the limiting phase, limiting current. And then you knock out, that drop again into the solution. So you can see it's a very interesting, type of chemistry, in the sense you are replenishing the electrode every time, which is very good. You're creating a new electrode every time. So you're renewing your electrode system. So that's why people really used to like it. Of course, the biggest challenge, is the toxicity, of mercury, and how to deal, with the disposal, of mercury. And that's why largely it's fallen out of favor. Because you're going to see one big challenge with the regular type of electrodes, is that they tend to foul over time, You put it in a dirty sample, it tends to get fouled or poisoned, over time. And so you need to actually polish it, especially the glassy carbon, especially the so-called glassy carbon electrode. The glassy carbon electrode, typically you need to keep polishing it, after a couple of times that you have used it, but in this case you can see, it replenishes itself. And, so typically, your profile will look like that. And as I said before, you look at, what the background current, and then the limiting current, and the gap, between the two is going to be your diffusion current, the ID, which is your analytical signal. And of course, after that, you can just do, your calibration, and so on. It's very important, for me to remind you, just like, a titration curve, where you've got, the pH being equals to, they have the have the pH here, gives you, the pKa, the point at which, you've got, the midpoint here, in your titration curve is sort of equivalent, to your pKa, all right? And I think that's a voltage, with the titration curves. So very similar, to that concept, in this case also, you've got the when the current, is at half maxima, when the current is at half maxima, you've got, the so-called E half right there, and that one is actually equivalent or very close, to the standard, reduction potential. So take note of that benchmark right there. When you've got, the half wave potential right there is equivalent to, what you call the standard reduction potential. And that's how they actually generate the standard reduction potentials, on the tables, that you actually see in chemistry textbook. And that I started with, in the second slide. That's how they actually determine it. I think I've already explained, this slide extensively, what is happening, to the solution, as the voltage is increasing. And then, of course, you get, to that midpoint that I talked about, the E half, which I said is equivalent to the standard reduction potential. And then you get, after you deplete all the analyte, in this case, say cadmium, is what you're trying to analyze in this case as an example. Cadmium gets depleted, from the electrode surface. And because of that, the current, plateaus off, and that becomes sort of the end, of your photometric signal. Now, with dropping mercury electrode, they developed these other sort of relationship, for the limiting current or the diffusion current, being proportional to concentration, based on this, constants. And of course, the reason for this is you're dealing with a liquid being an electrode. And so there are all these other factors that come into play, for the dropping mercurial electrode that are a bit different, when you're dealing with a solid state electrode. And this is what they call, Ilkovic, equation, which is specifically, based on polarography, for the dropping mercurial electrode. You can see, things like the flow, of the mercury through the capillary, get accounted for. Things like the diffusion coefficient, and so on. But as I said, it's only specific, the Ilkovic equation is only specific for dropping mercury electrode. Very quickly, some of the advantages, because there are still a few companies actually that still use dropping mercury electrode, so some of the advantages of using this type of polarography is because, of course, you're getting a fresh electrode every time. That's very, very good. And so you tend to get very reproducible results, because your electrode doesn't get poisoned as you do the chemistry. Another good advantage of dropping mercury electrode is it tends to be very, very clean, in the reduction range. So when you're doing the reduction, especially in the negative voltage range, it tends to be very, very clean, because mercury, tends to have a very high potential or over potential for hydrogen reduction. So mercury doesn't cause electrolysis, of water. And of course, electrolysis of water, really, really affects, your thermogram. But because of that, it's a very, very good electrode, in the negative range. Another good advantage, of mercury as an electrode is the fact that it forms solids, with specific heavy metals, like say mercury, when you bring it into contact with something, like cadmium 2+, it tends to form an amalgam. And an amalgam really is a solid, the stuff that people used to use for their dental fillings, and so on. And so because of that, you can actually do what you refer to as pre-concentration of the analyte, meaning I've got, my dropping mercury electrode there, and then I'm doing the reduction of cadmium, say, to cadmium metal. And then the cadmium metal, dissolves into the mercury, to create a solid. So you can see, I can actually pre-concentrate, my very small amounts of cadmium, onto my electrode. It's almost like you're doing electroplating, right? So you can do electroplating as a way to pre-concentrate, the sample, onto the electrode surface. And then after that, and I'm going to show you later in a couple of slides, you can actually do now the opposite of reduction, start doing oxidation, and then you can actually strip off, the metal, that was actually coated, on the electrode surface. And so based on that, as I'm going to show you later, you can really increase the signal, the limits of detection, using the anodic stripping type of technique, which is very commonly used, with a dropping mercury electrode because of its ability, to dissolve different types of metals. Some of the limitations, of course, is a very cumbersome technique. You're dealing with mercury and you're dealing with liquids. It's messy. Environmentally, it's difficult, to dissolve it. But even worse, is the problem of migration, the error that I talked about, the charging current. So remember, as a drop keeps growing, the charging current of that drop, keeps increasing. And because of that, that really affects the limit of detection. So in actual fact, you're going to see the polarographic curve typically looks like this. It's very, very, very unstable, very, very unstable, because the drop, keeps changing its size. It's almost like you're changing the electrode volume, over time. And so because of that, it's a very, it really limits, of course, your limit of detection because of that noise. So to solve the problem of the charging current, Ilkovic, developed these other technique, referred to as a pulse polarographic techniques, which is the basis of what we talked about, the differential pulse photometry and the square wave photometry. So we're gonna talk about that in the next lecture. Of how just by changing the potential steps of your profile, can actually reduce your charging current, and as such improve your limits of detection. And that's gonna be done in the next lecture.